All right, today we're cracking open one of the most powerful tools in all of science. It's kind of like a molecular detective, able to sniff out substances with just mind-blowing precision.
So let's just start with a question that sounds, well, impossible, right? How on earth do you weigh a single molecule? I mean, think about it. You can't see it, you can't touch it. It's this tiny, tiny thing. It's a puzzle scientists have been wrestling with for more than 100 years. And this isn't just some academic brain teaser. Answering this question is how we solve really critical, real-world mysteries every single day. Just think of it like a molecular whodunit. You're the detective, and all the most important clues are completely invisible.
I mean, how do you actually find that one performance-enhancing steroid in an athlete's blood? Or figure out if someone's been watering down pure honey with cheap corn syrup? What about identifying some unknown pollutant in your drinking water? Or even crazier, figuring out what molecules are floating around in the vastness of deep space? The clues are everywhere, but they're hidden in plain sight.
Well, the tool that brings all this to light, our molecular detective that cracks the case, is called mass spectrometry. And it's no exaggeration to say it is one of the most sensitive, most powerful techniques we have. It literally makes the invisible visible.
Okay, so what is this thing? How does it actually pull off this incredible feat of weighing something as tiny as a molecule? Let's get into it.
So at its core, you can think of mass spectrometry as this unbelievably precise scale, but for molecules. But here's the clever part. It doesn't just measure mass. It separates things based on something called the mass-to-charge ratio. And that ratio, that is the secret sauce. It's what determines exactly how a charged molecule is going to fly through a magnetic field. The best way to really get this is to just follow one molecule on its little adventure through the machine. It's a pretty wild ride, and it all happens in 4 main steps. Okay, step 1, get in. The sample gets introduced. Easy enough. Step 2, get charged. Now this part is absolutely critical. The molecules get zapped with a charge, turning them into ions. Why? Well, because you can't push or pull a neutral molecule with a magnet, right? You need that charge to steer it. Step 3, get sorted. Now that they're charged, the ions fly through the machine and get sorted based on that mass-to-charge ratio. And finally, step 4, get weighed. The sorted ions hit a detector, which counts them up.
All right, let's zoom in on that getting charged step, because this is where the real cleverness comes in. Scientists can use what's called hard ionization, and the analogy is perfect. It's like smashing a vase into a bunch of pieces. By studying the fragments, you can figure out how the original vase was put together. Or they can go with soft ionization. This is more like a gentle tap. It gives the molecule a charge, but leaves it pretty much intact, which is perfect when you just want to know its total weight.
Okay, so the ions have gone through the whole process. They're charged, they're sorted, they're counted. What's next? Well, the machine spits out a chart, a unique plot for every single substance. And this, my friends, is where the case gets cracked.
This chart is called a mass spectrum, and you really should think of it as a molecular fingerprint. It's the ultimate identifier because just like a human fingerprint, every single molecule has its own unique pattern. No two are exactly alike.
So when we're looking at this fingerprint, the first big clue is something called the molecular ion peak. If we're sticking with our detective story, this peak, this is our suspect, totally intact. Its position on the chart tells us the total mass of the entire compound. It's our first and maybe most important lead in the case.
The next major clue is the base peak. Now this one's easy to spot. It's always the tallest peak in the entire spectrum. It represents the most common fragment, the piece of evidence that shows up the most when our molecule breaks apart. So we just set that peak's intensity to 100%, and then we measure every other fragment relative to it. It gives us a full, detailed profile of our molecular suspect. So okay, now we know how to read these molecular fingerprints. And with that ability, we can solve an absolutely mind-boggling range of cases. I mean, from things happening inside a single cell all the way out to the stars. And you have to remember, this incredible tool didn't just pop into existence. It's been evolving for more than 100 years. It started out back in 1919, proving that elements could have different masses. Isotopes. Then came the real game changers, techniques like electrospray ionization and MALDI. These breakthroughs opened the door to weighing huge biological molecules, which totally revolutionized fields like medicine and biology. And just look at its reach today. It's everywhere. In medicine for developing new drugs, in food safety for spotting pesticides, in forensics for identifying drugs, environmental science, archaeology, even biotechnology. It's become this absolutely essential tool because it finds the clues that nothing else can see.
You know, there's a famous quote from a big chemistry textbook that says mass spectrometry is perhaps the most widely applicable of all the analytical tools available. And think about that for a second. That is a huge claim, but it's not an exaggeration. This technology has fundamentally, totally changed how we see and understand the world on a molecular level.
So let's just recap. We have a single tool that can help identify markers for disease, that can literally read the history of our planet from a tiny sample, and can even tell us what distant stars are made of. The number of cases this molecular detective can solve is really only limited by what we can imagine. Which leaves us with one big question, right? What mysteries will it solve next?